Welcome to AP Calculus BC video for skill number 238. I can use calculus to sketch functions. Alright, in this skill we're kind of pulling together all the things that we've learned about functions and using calculus to create a nice clean drawing of the function. And for me, this is the list of all of the things that I want you to find while generating a clean drawing of the function. X-intercepts, y-intercepts, horizontal asymptotes, vertical asymptotes, holes, increasing and decreasing intervals, concave up, concave down intervals, the local min and max, and points of inflection. So, some of these require calculus and other ones are just algebra skills. So I'm going to walk through one example and just kind of demonstrate what it takes to find all this information. Alright, so first we're going to find all the necessary info listed above, and I've made a copy of it over here, and use this to sketch the function f of x equals quantity x plus 2 over x plus 3 squared. So to find the x-intercepts, we're going to set the function equal to 0, and the function is going to be 0 if the numerator is 0. So we have an x-intercept at -2, 0. Algebra skill. Find the y-intercepts by letting x equal 0. So essentially we're finding what is f of 0. And we find f of 0 to be 4/9, so we have a y-intercept at 4/9. I guess technically we can only have one y-intercept, so this should say y-intercept. That is an algebra skill as well. Find horizontal asymptotes by taking the limit as x goes to infinity or -infinity of the function. If we took our function and rewrote it as x plus 2 squared over x plus 3 squared, we would see that our leading terms are x squared and x squared, and if we take the limit as x goes to infinity of that, we're going to get 1. So we only have one horizontal asymptote, and that is at y equals 1. So that is a calculus skill. Alright, so now we found the x-intercept, the y-intercept, and our horizontal asymptotes. And now we're looking at our vertical asymptotes. And to find our vertical asymptotes, we're going to look at domain restrictions, because domain restrictions oftentimes will mean there is a hole or a vertical asymptote. And in our particular function, we had x plus 2 squared on top and x plus 3 squared on bottom. The only domain restriction we have is at -3. So I'm going to evaluate the left-hand limit of the function and the right-hand limit of the function. I see they both go to infinity, so that tells me we have a vertical asymptote. If they approached the same number, then say they both approach 2, then we would have a hole there. So that brings us to the next part where we're finding holes by examining the domain restrictions. There's no factors that cancel. Our right and left hand limits don't tell us there's a hole, so we can say there are no holes. An example of an equation that might have a hole would be x plus 2, x minus 1 over x plus 2, x plus 5. And notice that these two terms cancel, so we would have a hole at x equals -2. Okay, the next part is finding increasing and decreasing intervals by finding the critical values and using the first derivative test. So if I take the derivative of the function and I applied the chain rule within the quotient rule, I was able to find that we have critical values of -2, which I found by setting it equal to 0, and then also the critical value of -3. So we also want to look at parts where the function is non-differentiable. So with those two critical values, I set up a table, and I use that table to find whether it's increasing or decreasing. And so what I did is I drew the table. Let's do it in red. I drew the table and I said I have the value of -3 and I have a value of -2, and I'm going to test values in each interval. And I saw that within the interval less than 3 it was positive, the interval between 3, -3, and -2 it's a negative, so it's decreasing, and then the interval after -2 is positive, so that would be increasing. So now I found the increasing and decreasing intervals, and from here I can find concave up and concave down intervals using the concavity test. So if I have f prime, I can find f double prime, and I set f double prime equal to 0 to find potential points of inflection. And again, we're going to look at that number outside of the domain. The numerator in this case is actually a pretty nasty numerator, but if you go through and kind of distribute the 3 in and you do some factoring, you'll find that you can actually solve the other point to be -3/2. And so I need to create another truth table for -3 and -3/2, which we do on the next page. And using the concavity test, I've created the interval from -3 to -3/2, and I do test values for f double prime. And each of those test values gives me concave up, and then concave down. So now I have my intervals of concavity. And then I can combine this with my second derivative test and look at the critical values. F double prime of -3 does not exist. F double prime of -2 is positive. So we know that we have a local minimum at x equals -2. And if I evaluated the function further, I would see that the local minimum is -2, 0, which actually is our intercept as well. Finally, we look back at the concavity test to determine points of inflection. Because we're switching from concave up to concave down at -3/2, we have an inflection point at x equals -3/2. And if I want to know the exact y value, I can plug -3/2 into the function. Alright, that is all the pieces that we have to find, and now we can pull it all together to make a graph, which we'll do on the next page. Alright, so right here what I've done is I summarized all of our findings down below, and then I'll walk us through how I graphed it. So the first thing I did was I plotted the x-intercept at -2. The next thing I plotted was the y-intercept at 4/9. And then I plotted an inflection point at -3/2, 1/9, so approximately right there. Then I plotted my horizontal and vertical asymptotes. So I had a horizontal asymptote at 1, so this is this horizontal line, and a vertical asymptote at -3. So now I've got my kind of boundary set, and then I can find that I've got concave up from -infinity to 3. So that tells me that I have to be in this area here, and I can kind of draw the arrows so that I stay within the boundaries of my asymptotes. And then I also have concave up from -3 to, there should be a negative right there, -3, -3. So then I also have concave up from -3 to -2. And actually we keep going to -3.5, so that's all concave up. And then we move to concave down on the other side of that point, so this is all concave down, and that's how we stay underneath the asymptote there. I double check with that my intervals of increasing and decreasing, and I see that I am increasing from -infinity to -3, and I am increasing from -2 to infinity. And then finally I am decreasing from -3 to -2. Again, please note that we have this -3 here. I made a mistake writing that down, so make sure you catch that in your notes. Alright, so the skill test for this is going to be very similar to what we just did. You will be given some function, and you will be asked to use calculus to evaluate the function and find increasing, decreasing intervals, etc. I'll probably keep it a relatively tame function like the one I've drawn here. But we need to be able to find all those pieces. I will provide you with the list of the things that are needed, so you can go through and check off as you move along. But it will be a closed note quiz or skill test. So good luck, and I'll catch you later. Thanks for watching.